All right, we ready? Let's go ahead and get started. 2014 AP Chemistry Free Response question. Electrochemistry. I know. I'm excited. I like electrochem. This is your least favorite? Is electrochem? All right. This was question 3. This was the first year they redesigned it in 2014. So we only have 2 redesigned questions, 2014 and 2015. Those are the only 2 exams we have that are like what they're giving y'all now because they redesigned it in 2014. So I am pretty sure your mock exam is going to be what last year's real exam was for them. So that'll give you an idea of, yes ma'am?
I know, I'm waiting on it. I'm working on it.
Okay.
They're making a bunch of copies in the office. So.
Oh, okay. All right, so let's go ahead and get started on this. A student is given a standard galvanic cell represented above that has a copper electrode and a tin electrode. As current flows through the cell, the student determines that the copper electrode increases in mass and the tin electrode decreases in mass. A says identify the electrode at which oxidation is occurring. Explain your reasoning based on the student's observations. Okay, so let's talk about this. Let's just look at this cell and let's break it down. Okay, so I've got 1 molar tin 2 nitrate. How do I know it's tin 2?
Because you just a little swamp and
There you go, because we uncrisscross to get the charges, right? Okay, so that 2 goes with, that means the 10 is positive 2. Since there's not a subscript here, I know that nitrate's what? Negative 1. Does everybody see that? Okay, so this 2 means this is copper 2 positive. That means this nitrate's negative 1. Right? We see that? We're good? We're good. All right, so that means in this solution, I've got SN2 positive, NO3 negative. I've got Cu2 positive, NO3 negative. The NO3 negatives we don't really care about, so we can just pretend like they're not there. Okay. Now, this tin electrode is losing mass. This copper electrode is gaining mass. Okay. So, which one is being oxidized? The tin. Okay? How do I know it's being oxidized? If it's losing mass, that means the solid tin, the solid SN on this electrode is doing what? How is it losing the mass? That means it has to be losing what? Electrons, right? Yes? Everybody see that? It's losing electrons. So the solid tin is going into solution as what? SN2 positive. Okay, how do I know it's going in as SN2 positive? Because that's the solution they gave me. Right? Yes? Right. So this side is gaining the electrons. So the negative electron charge builds up in this electrode, and every time one of these copper ions touches the electrode, what happens? They turn into what? They turn into what? It just turns into copper, right? So these ions turn into copper, which is why the copper electrode is gaining mass. Does that make sense? Yes? Okay. So, A says identify the electrode at which oxidation is occurring, the tin electrode. Explain your reasoning. The tin electrode is losing mass because tin is becoming SN2 positive. Is that oxidation when something becomes more positive? Mm-hmm. Yes, because remember, oil rig, oxidation is loss of electrons. Reduction is gain of electrons. Okay? When I lose electrons, I become more what? Positive. When I gain electrons, I become more negative. My Sn, which has a charge of 0, okay, is losing electrons and becoming Sn2 positive. Do we see that? So it's being oxidized. My copper ions in solution, Cu2 positive, are gaining electrons and just becoming Cu metal. Do we see that? Yes? Okay. As the mass of the tin electrode decreases, where does the mass go? You should know this now. I just answered it. No. Okay, it's going into the solution as what? As Sn2 positive. Yes? All right. So, let's keep talking about this. So this side is losing electrons, and I'm constantly getting more and more what? Sn2 positive. So this is becoming more and more positive. Okay? On this side, I'm constantly losing all of my positive ions because they're turning into what? Copper. So this side is constantly becoming more what? Negative. What do I need to do to balance out the charge in this cell so it keeps going and going and going and giving me salt bridge? Since this side is becoming more positive, what needs to go into this side? Negative. So my salt bridge is made out of KNO3, so what's going to go in this side? NO3 negative, right? And what's going to go into this side? K positive. Do we see that? Yes? So, question C says, in the expanded view of the center portions of the salt bridge shown in the diagram below, draw and label a particle view of what occurs in the salt bridge as the cell begins to operate. Omit solvent molecules and use arrows to show the movement of particles. That just means they want you to show that K positive is moving towards copper and NO3 negative is moving towards the tin. Like we just did. Does that make sense? Your mock exam is March 31st and you're going to be graded on it. So, these are review packets for you to use to help you out. No, you don't have to write. You're good. Does everybody see this so far? So now that we've gone over it, if you saw something like this on the exam, you could handle it, right?
Are you going to grade the free response? Or are you going to grade the whole overall?
The whole thing.
Nice. That's cool.
Okay.
Because I know
All right, so far, A would have gotten you 1 point, B would have gotten you 1 point, and C would have gotten you 2 points. Huh?
Why two?
It would have gotten you a point for recognizing that they split up into the positive and negative ions, and a point for having them going in the right direction. Okay.
At least good that you're grading it like it's supposed to be though, because it actually like it'll show us where we're going to be at.
Exactly.
Like, Ms. Elrod said 100.
Yeah, but you could- Yeah, but you could tell us where we're at without us actually failing your class.
Yeah. I'm not going to make you fail. You're going to be fine. You're going to be fine. All right.
I kind of can't fail this, but I need to graduate, so.
D says a non-standard cell is made by replacing the 1 molar solutions of copper 2 nitrate and tin 2 nitrate in the standard cell with 0.5 molar solutions of copper 2 nitrate and tin 2 nitrate. The volumes of solutions in the non-standard cell are identical to those in the standard cell. Before you can begin to answer these questions, you need to know the difference between standard and non-standard. Okay? A standard cell just means that both solutions are at 1.0 molar. Okay? So notice up here in the original problem, I had 1 molar and 1 molar solutions, right? Do we see that? That's a standard cell. So now we're saying, what if we don't change anything else? All we did was change this 1 molar to 0.5 molar. That now makes it a non-standard cell because it's not at 1 molar. Okay? So don't let the wording there freak you out. Okay? It's not freaking you out. It's just saying we changed it from 1 molar to something else. Is the cell potential? Okay? So the cell potential, the amount of voltage the cell has the ability to produce, okay, of the non-standard cell greater than, less than, or equal to the cell potential of the standard cell. Justify your answer. Okay. It's okay. We're going to talk about it. Okay, the cell potential is going to be equal to the same cell potential it is when it's 1.0 molar. Okay? Why? What do I use to help me get my cell potential? This is where our good old buddy Q comes in. Okay? Q comes in here. So Q is equal to concentration of products over concentration of reactants, right? And we omit solids and liquids, right? Yes. So let's go up here. All right? Here's my reaction on this side. Here's my reaction on this side. Okay? Now, if the metals have a charge of 0, that means they're in what state? Solid. Okay? So we've got to omit those, right? I said the Cu2 positive, as soon as it touches the electrode, it becomes copper and sticks to it. Correct? Yes? All right, so who is my reactant then? Cu2 positive. And my product is SN2 positive. Do we see that? Yes? Yes. Okay. So, if Q is equal to the concentration of products, SN2 positive, over the concentration of reactants, Cu2 positive, it doesn't matter that I decrease the concentration by half. Both of these concentrations are still the what? Same. If I do 1 divided by 1, what do I get? 1. If I do 0.5 divided by 0.5, what do I get? 1. Do we see that? So the cell potential does not change. It remains the same.
So the equation would be your justification.
Yes. Your equation is your justification there.
Would you have to like plug your numbers or just put?
So you would just say this, and then you would say the concentrations are equal. So the cell potential stays the same. Plus 1. And I will tell you, when we get finished with this question, I think you will see that you could have done A, B, and C, and you could have done E. And you probably would have gotten stuck if this was the real AP exam on D, and that's fine. That means you missed 2 out of the 10 points. If you get 8 out of 10 points on a free response question, we are all going to shout glory hallelujah. Okay? Like, we are not going to be upset over this, because remember, we're shooting just to get what? Half. Okay? We're trying to get 75% of the multiple choice, and we're trying to get half of the free response. Now, some of you know you're not going to be able to get 75% of the multiple choice because for some reason, y'all are better at free response than you are multiple choice, which is fine. So that's when we're going to grab extra points where we can. Like on this question, we'll see, okay, I probably could have done A, B, C, and E. D, I probably couldn't have done. And if you would have read that question right there and you didn't know the answer and you knew you didn't know how to get the answer, make your best guess, write some bull, and move on. Okay? All right? And maybe you'll be right, and maybe you'll be wrong. It'll be okay. It's 2 points. I tried my best. I'm going to get the 8 points I know I can get first. Does that make sense? We're not going to sit there and stress about something we don't know.
Will they give us a point or anything for, is there any things that we can do to our answer where we'll at least get a point for it, whether it's completely wrong or not?
Some of them, they'll give you a point for the answer and then a point for the explanation. So that's why I say always guess just in case it's one of those questions.
Like if it was 3 sentences or less, you got a point for having 3 sentences.
Oh, yeah, no, they don't do that. Okay.
I was just wondering if they ever do anything.
No, they don't do anything like that. All right, 2. Both the standard and non-standard cells can be used to power an electronic device. Would the non-standard cell power... Don't switch that desk out. I sent Spencer all the way around the world to get desks this morning, and that's the one he wants, so I'm not moving it from his spot because he did me a favor. So it's just going to say. All right. Would the non-standard cell power the device for the same time, a longer time, or a shorter time as compared with the standard cell? Justify your answer. Okay. So, question is, put it in simple terms, changing the concentration to 0.5 molar. Is this going to power the cell for a shorter time, longer time, or the same amount of time? Shorter. It's going to be shorter time. Okay. Remember, where am I getting my voltage from? From my electrons flowing and my ions moving around, correct? Right? When I changed it to 0.5 molar, that means I've got less what? I've got less copper ions here, right? So what's going to happen when I run out of copper ions? The cell's going to stop, right? My E naught is going to reach 0. I am at equilibrium. Nothing's going to happen. Does that make sense? Are you with me? Yes? So, at that point, the cell stops. So, if I lowered my concentration, that means I lowered the number of Cu2 positive ions, which means the cell can give me the exact same power, it's just not going to power it for as long. Does that make sense? Yes? Okay, shorter time. So there are less Cu2 positive ions, which means E naught will reach 0 faster. And we all know what happens when we reach 0. That means we're at equilibrium and we are dead. All right, E. So if I got stuck on D, that's cool because I just read E and I got pumped. Okay? Or that's what happened when I did the free response packet. You got pumped too. I'm just going to say it in my head. You got pumped too. I know you did. All right, so in another experiment, a student places a new tin electrode. Notice this tin electrode must be what? State of matter. Must be a solid, right? Because it said they put the tin electrode. So the electrode was made of tin, which means it had to be solid. Into a fresh solution of 1 molar copper 2 nitrate. How do I know this is copper 2? I do the opposite crisscross. So just that sentence right there should let me know which 2 of these equations I'm going to use. I am going to use this one. Why? Why am I using this one versus the one above it? These are both what? Ions. Are ions solid? They are not in the solid state of matter. Can I stick an electrode of SN4 positive into a solution? No, it wouldn't be an electrode. Okay? So therefore I know that this can't be the equation that they were talking about I used. Does that make sense?
You have to do the copper 2
Okay.
positive.
And I know that this was copper 2 because it's copper 2 nitrate, so I know I'm using this one, not this one. Does that make sense? You with me? Everybody see that? Okay. 1. Using information from the table above, write a net ionic equation for the reaction between the tin electrode and the copper 2 nitrate solution that would be thermodynamically favorable. So let's do that first. All right? So let's do the net ionic equation. So when we do the net ionic equation using half reactions, we want those electrons to cancel, which means I need to have some electrons on the reactant side and some electrons on the product side. So when I look at both of these, I see that the electrons are both on the what? Reactant side. So I know one of these has to flip. Right? One of them is reduced, stays the same. One of them is oxidized, so we flip the equation.
And then, right,
Yeah, you switch the SU to equals 3 because the voltage or the is negative.
There you go. Most positive gets reduced. So the one with the most positive gets reduced.
I feel like I'm learning something because I had the hardest time with this.
Okay. So the most positive gets reduced, and this happens at the cathode. Just as a quick lesson, because red cat reduction occurs at the cathode. Yes. Yes. Okay. The most negative. Now, does that mean the number has to be negative? No. It just means it's the one that's closest to 0. The most negative gets oxidized. This happens at the anode, so we call it an ox. Red cat and an ox. You have that in every reaction. A red cat and an ox. Reduction occurs at the cathode, oxidation occurs at the anode. Got it? Okay. So, that means we take the oxidized equation and we flip it. Okay. We take the reduced equation and it stays the same. So that means I'm going to take this equation and change it to Sn solid goes to Sn2 positive plus 2 electrons. And so now this negative 0.14 voltage becomes a positive 0.14 voltage. So now those are the two equations I'm going to use.
That says S, right?
Yes. Everybody see this? Yes? All right. So, will my electrons cancel now?
Yes.
Yes. If they would not cancel, like let's say I had 3 and 2, then I would have to multiply to get them the what? Same. Do I change my voltage when I do that? No. The only time you multiply your number values when you change those is when we're doing like delta H and K. Okay? Not when we're doing E naught. So, my electrons cancel. So now my net ionic equation, and we'll do that down here, is going to be Cu2 positive plus Sn goes to Sn2 positive plus Cu solid. Does everybody see that? Yes? And I just got myself a point. All right? Now, justify that this reaction is thermodynamically favorable. Let's go over our favorable conditions one more time in life. My E naught has to be, my delta G has to be, and my K has to be greater than 1. Okay? Remember, if we don't remember anything else in life, please remember those 3 things. Okay? If it is favorable, that's what has to happen. So, how do I find my E naught value? I add them both together. You add the reduction plus the oxidized. So I have 0.34 plus 0.14 is equal to 0.48 volts. Since my E naught is positive, I know this reaction is what? Thermodynamically favorable. Plus 1.
Can you take them off of them? Like she said, like I asked Miss Elrod that, she said you could take them off because I wanted to know if she could pass one. Like, but I wanted, like, you know, obviously I feel like you passed it. Could you take it?
Could I take it?
Yeah.
I kind of did last year. I took it with me.
Did you?
You should do that this year. And then
What'd you
when
make?
You should sit
I just
down.
wanted to know what it was
Sit by me.
for.
What'd you
You
make?
should take it and sit
I don't think I got a 5. I think I got a 4,
No.
if I remember correctly. Yeah, I didn't get a 5 when I took it.
Maybe you learned a little since then, so you should take it with us.
What'd you say, Olivia?
No, Coach said, really?
Oh. I didn't get a 5. Well, last year we didn't get as far in the course as like we did now. Like last year we were trying to cram in units at the end.
It was also your first year teaching.
Yeah, it was, I mean, we were just trying to like,
They didn't care.
And they didn't care. It was just a big, like, I didn't even have all the material I needed when I took it. This year, I think I can get a 5. That's my goal.
Do it with us. I'll take it with us. Take it with us.
I'm going to get my 5. All right. So,
We're hiring.
Tell me how it feels.
I'll let you know.
Let us know how you feel.
All right, 2 says calculate the value of delta G for the reaction. Include units with your answer. Okay. Now, when they say to include units with your answer, you better be putting some units with your answer because that is their code for we are not giving you credit without units. Okay? It doesn't matter if you get the number right. They're not going to give you credit if you don't have units. Okay? So, calculate the value of delta G. Oh, crap. There are 1,000 equations for delta G. I don't remember which one, so that's why I look on my equation sheet because that's why they give it to you. Yes? Yes, that's why they give it to you. So if you look on your equation sheet, it says delta G is equal to delta H minus T delta S. Delta G is equal to negative RT times the natural log of K. And delta G is equal to negative NFE. So which one do you think we're going to use? Negative NFE. Okay, do we see that? And it's on my equation sheet, so there's no reason why I can't come up with an equation to use here. Okay, so delta G is equal to negative NFE is what we're going to use. What is N? Moles of electrons. So in this reaction, how many moles of electrons am I using? 2. How did I get that? Because that's the number that I canceled. It's 2 electrons. Do we see that? If I would have had to multiply it on both to get to 6 electrons, then N would have been 6, because that's the number that I canceled, okay? So whatever number you cancel is your moles of electrons. So that means I'm using 2 moles of electrons for every mole of this reaction. I'll show you why I did that in just a second, okay? And it'll make sense. F is Faraday's constant, which is 96,485 coulombs per mole of electron. So now I can already see my moles of electrons have what? Canceled. That's on your equation sheet as well. Faraday's constant. You don't have to memorize that. It's on your equation sheet. Okay. And then your E value, we just found to be what? 0.48 volts. But wait, volts isn't up there. I'm going to start having a panic attack. It does not cancel. But no, I'm not going to have a panic attack because I look on my equation sheet and it says 1 volt is equal to what? 1 joule over coulomb. So this is 0.48 joules per coulomb. So now my coulombs have what? Canceled. So if I put this in my calculator, and I do some rounding, I would have gotten negative 93,000. What are my units here? Joules per mole. Do we see that?
Sometimes I really think of you saying that, like when I take a test, I'm like, we're not going to freak out. We're not going to freak out.
We're not going to freak out.
I can hear you saying in my head, like when I take a
We're
test.
not going to freak out.
The moles of the reaction.
The moles of reaction, because when we get delta G and delta H, we always want the units to be in kilojoules per mole. Okay? Because the whole reason why we do this, remember when we take our delta H's and we can change the equations, like we can flip them and we can multiply them, and whatever I do to the equation, I have to do to delta H? That's because, like, let's say if I had H2 plus O2 goes to 2 H2O. Okay? And I say that the delta H of this is equal to 4. Obviously, it's not. I'm just saying it is. Okay? And then I say, well, I multiply this whole equation by 2, and I change that to 4 to 4. Now my delta H is equal to 8. What's it equal to? It's 8 kilojoules per mole. Why do I want it to be per mole? Because I changed the number of moles I had when I multiplied that equation.
Yeah, how do you know though you're supposed to put moles of reaction under the 2 moles of electron? Like, how do you know you're supposed to put that right there?
You wouldn't have to know that you were supposed to put it right there as long as you remembered that delta G and delta H are per mole. They're whatever my energy unit is per mole. Okay? So that's why I showed the moles there to show you where they get that. They get that because they're saying there's 2 moles of electrons per every reaction. Does that make sense? Because really in the reaction, we're transferring way more than 2 electrons, right? I mean, we're transferring 2 and then another 2, then another 2, then another 2. We're just saying per reaction, I'm getting 2. Does that make sense? Okay. Now, second thing to remember, make yourself a note on here. They like delta G and delta H to be in kilojoules per mole. So, I'm not saying they would count off, but if you can just remember that, just come back 1, 2, 3, and make that a negative 93 kilojoules per mole.
And when you do that for mole, you have to write like moles of reaction because on the little thing that I was looking at, like helped us.
Yeah. You don't have to. You can write per mole, and they'll count it just the same. Mm-hmm. Yeah, Bella came in the office Thursday and said, we looked up the answers and tried to work backwards, and it still didn't work.
No, I was telling her about how you didn't know how to do anything.
So,
Well, I mean, we did all the time, we had to do it.
Yeah.
We didn't like.
I just gotta make it stick.
It's so hard to recall.
and then you would have gotten 1 point for recognizing it was 2 moles of electrons, and 1 point for getting the correct answer.
How mad would you have been if you played your board?
What word do you have?
We thought about that.
No, I would have actually been happy because it needs to be clean.
Yeah.
Oh yeah.
All right, let's do the equilibrium one, and then we'll do the second one tomorrow.
The one on the very bottom.
Yeah, the one on the very back.
Right.
All right. A sample of solid U3O8 is placed in a rigid 1.5 liter flask of chlorine gas. Cl2 is added and the flask is heated to 862 degrees Celsius. The equation for the reaction that takes place and the equilibrium constant expression for the reaction are given below. So they gave me my balanced reaction. They also gave me my Kp value. Notice they took out the solid because who do we not include in our equilibrium expressions? Solids and liquids. And they took the coefficients and made them what? Exponents. They made them the powers. Now, the reason why I'm going over that is because you see how they gave this to you. Sometimes they will, sometimes they won't. Sometimes their first question will be, write the equilibrium expression for this reaction. Okay? Which should get you excited, because that's an easy point. So we're okay with that. All right? But just make sure that you remember how to write it. Okay? When the system is at equilibrium, the partial pressures of Cl2 is 1.007 atmospheres, and the partial pressure of UO2-Cl2 is 9.74 times 10 to the negative 4th atmospheres. Now remember, these are their pressures at equilibrium, which is code for I need to make a rice table. Okay? That's what that is code for. So I find a good spot on my paper where I can write myself a little note. And I say, okay, self, I can do this. I'm going to go back to what good old Snellick told me. And I am going to be okay. Yes, I am, self. Oh, no.
That's probably gonna be me.
No, we're not going to tell self to have a panic attack.
Yeah, and I think so. No, I'm myself to take a nap.
Okay? All right, so here's my R. Initial. Now, I don't care about this one because it's a solid, so I'm just going to X myself right out of that. All right? Does it give me any initial concentrations? No. So I don't know what the chlorine is, and since they didn't give me initial for products, I'm going to assume that they are at what? 0. Right? So, change. I know I'm going to lose 3x, I'm going to add 3x, and I'm going to add X. At equilibrium, did they give me some values? Yes, they told me that the chlorine is 1.007, and they told me that this UO2Cl2 is, somebody read it for me,
9.734 times 10 to the negative 4.
times 10 to the negative fourth atmospheres. I guess I can put units so I don't forget. And then they don't tell me oxygen, that's what I'm trying to find, so oxygen is just X atmospheres. I don't know how many, but can I figure that out now?
Yeah.
Yes, how can I figure out X?
Alright, hang on.
Yeah. I'd go with
For the,
Do the brush.
you take the, for the UO2CO, so you just divide it by, and you divide it by.
Remember, at equilibrium, E is equal to I plus C, right? Yeah, your initial plus your change. So that means at equilibrium, this is 0 plus 3x is equal to 9.734 times 10 to the negative fourth atmospheres. Can I solve for x? Just divide by 3, right? So I take this and divide by 3, and my x is equal to 3.245 times 10 to the negative fourth atmospheres. And I get a point. Okay, huh?
7.4 rice, and if they were just, that'd be good.
Now, why could I not use this one?
You don't know you got a question?
Here you go. I don't know the initial. Okay? So knowing the initial could completely change my value for x there. Does that make sense? Yeah. So we have to use that one. So question B turns right around and says, okay, so now calculate the value of K. Can I do that? Do I know all of my pressures at equilibrium now? Yes. So I just say, okay, well, Kp is equal to products over reactants. So I'm going 9.734 times 10 to the negative 4. And I'm going to cube that, correct? Yes, because there's 3. Times, I now found oxygen to be 3.245 times 10 to the negative 4. Divided by 1.007. And I'm also going to cube that, because there's 3 there. Does everybody see that? Do you also see how if you got stuck on A, you better come up with some janked up way to find what oxygen is and use it and plug it into the next one so you can at least get a point for it. Okay?
Oh, yeah, because you still get a point.
Because you still get a point.
Yeah.
They don't hold against you that you got it wrong in A if you still knew what to do with it in B. So come up with something.
So just come up with a number.
Yeah, I mean, use the numbers they gave you to somehow do something to get some other number. Does that make sense? Okay? And I got my number, and I'm going with that number, and I'm going to be confident with that number. Okay? And it may be the completely wrong number, but it doesn't matter because it still got me a point. Check me out. Okay?
I'm going to write that all the time.
Does this make sense?
Yeah.
Yes. All right. So the answer is 2.931 times 10 to the negative 13. You would have gotten 1 point for just plugging in the stuff correctly and 1 point for getting the answer.
But we already got 3 points.
Check us out.
Well, Selick already got 3
Forgot about
points.
the last one. The last one, so we're up to
We can
4.
at least get 2.
Exactly. Y'all should have at least been able to get 2 points there. C asks you to calculate Gibbs free energy, delta G. So I go back to my equation sheet, which I wrote down here. So I'm going to come back to this page. And I look at my 3 equations for delta G, and I say, all right, which one am I going to use? There you go. Negative RT times the natural log of K. I'm using that one because I just found what? K. So that must have been the equation that they meant for me to use.
Ours is constant.
Okay. So delta G is equal to negative RT times the natural log of K. So delta G is equal to a negative. R is a constant. Okay. Now remember, Delta G, I'm wanting in units of kilojoules per mole. So that means I need some sort of what? Energy there. So what R value am I going to use for my equation sheet? The 8.314. Okay? Remember, we're using the 8.314 because the units there are what? Joules over moles times Kelvin. So that's where I'm going to get my energy from. Does that make sense? Yes? Okay. Times, since this is in joules over moles times Kelvin, what does my temperature have to be in?
98
Kelvin. So I've got to take that 862 and I've got to do what? Add 273. And that gives me 1,135 Kelvin. So notice my Kelvins are going to what? Cancel.
That's really, really hot.
Times the natural log of 2.931 times 10 to the negative 13th. So if I put all of that in my calculator, I would have gotten 272,000 joules per mole. Do we all see that's joules?
I guess.
But what do I like my delta G to be in? Kilojoules.
Some of the best.
So I come back and say that's 272 kilojoules. Okay? 1 point for setting this up correctly. 1 point for getting the answer.
That's what I'm just setting it up correctly.
I mean, if you set it up correctly, you ought to get the right answer.
Well, not if you got.
Sometimes you don't,
previous
though.
ones.
Okay? Some people just mess up.
But they have a calculator, and as long as you get the right answer to the numbers you plugged in, you get the 1 point.
Mm-hmm.
Well,
All right. D says state whether the entropy change, delta S, for the reaction at 862 degrees Celsius is positive, negative, or zero. Justify your answer. Remember, if delta S is positive, it became more disordered. If delta S is negative, it became more ordered. And if it's zero, it just didn't change. Okay, so let's look at this equation that they gave me up here. In this equation, did I become more ordered or more disordered?
Disorder, because you went from a solid to a gas.
There you go. I became more disordered. I went from a solid to what? Two gases. Does everybody see that? And that would be a point, and we'll finish this tomorrow. Have a great and lovely afternoon.